So, answering this question, we know that the ring has a total charge of Q. And we know, as it has a radius of A, that the line density, which is lambda, equals the change in charge over the change in x, which is the change in radius. And as it's a circle, perpendicular, not a circle circumference, we know that this equals Q over 2 pi A. This is like 2 pi r is the circumference over the perimeter of the circle. So we know we have line type geometry here, as we have lambda, and it's not a surface or a volume, it is a line, so we use lambda as our line density. And then we have the following expression for the electric field of this ring. As line density is constant, we can bring it out to the front. Then we have r minus r thingy over r minus r prime cubed dl prime. Although this problem does look like a cylindrical problem, we can just consider it in Cartesian form. And so we know that our point R is equal to 0, 0, z, as it is only on the z direction. It is just further up the line. There's no change in the x or y. And then we know that our r prime can be summed as a cos alpha prime, a sine alpha prime, and then 0, as there's no change in the z direction. So we know that we need to find r minus r prime, so we can just write this as minus a cos alpha prime I hat minus, so that becomes a plus, a sine alpha prime j hat plus z k hat. And then our denominator, which is below, so r minus r dash cubed equals a squared cos squared alpha prime plus a squared sine squared alpha prime, sorry I'm a bit ill, plus z squared over to the power of 3 over 2, because we cube it but we need to square root it because we are finding the distance, the absolute value here. So this just simplifies to get a plus z squared, a squared plus z squared, all to the power of 3 over 2. Now, we know with this, we've simplified that because we know that a cos squared alpha prime plus sine squared alpha prime equals 1, and so it just simplifies here. Apologies. So, we know that if we take an infinitesimal small element of the circle, we have the arc length of L dash equals a alpha dash prime, and so that dl prime equals a change in alpha prime d alpha prime. So then we can put this all back into our equation up here, and we see that the electric field of R equals 1 over 4 pi epsilon naught theta, and then as it's a circle, we're going to go 0 to 2 pi, so we're going to have 2 pi up here and 0 down here, minus a cos alpha prime I hat minus a sine alpha prime j hat plus z k hat, all over our value we got here, so a squared plus z squared 3 over 2, and then because we got our dl prime, we know that that's just a d alpha prime. We can tidy this up a bit, and we can bring some things out to the front. So we get the electric field is equal to 4 pi epsilon naught lambda times 2 pi a z, as we're bringing some of this out, and we're simplifying. Oh, sorry, I skipped a step there. Sorry. A over this bottom bit, a squared plus z squared 3 over 2, and then we have our integral again, but we're only considering the numerator at this point because we've taken the denominator out. Cos alpha prime I hat minus a sine alpha prime j hat, and then we got plus z k hat, all with d alpha prime. So then the integrals of cos alpha prime and sine alpha prime between 0 and 2 pi both 0, so then the x component and the y component of the electric field is 0, so then we get just z k hat delta alpha, which integrates to 2 pi z. So then our electric field then comes to 1 over 4 pi epsilon naught 2 pi alpha a lambda z over a squared plus z squared 3 over 2 k hat, which then, because we know that our 2 pi a lambda from this beginning up here is equal to q, we can simplify this and write 1 over 4 pi epsilon naught qz over a squared plus z squared to the power 3 over 2 in k hat direction. And so we see that the electric field is only equivalent in the z direction. So from the point what we're measuring from, we just see it gets feels the effect from that side. So yeah, that is our answer here. This is the electric field of the ring of charge. I hope that made sense. Make sure you hit like and subscribe, and I'll see you guys in the next video. Goodbye.